Alright, looks like we are live. Okay. Let's continue. Let me open the table of content first. Okay. We already we are still in chapter 5 on homework code here. Okay. Yeah, on this section, and currently we are in this question. It is basically how to ensure the chat process always print first without calling wait or wait PIT in the parent process. Let me open my terminal. Okay. I have a few solutions. If I remember correctly, 3 solutions. Right. The first one is using select to block the, what is it called? To block the parent process according to the timeout. In this case, not that one. In this case, 10 seconds. This is second and this is microsecond. Again, you can take a look at the manual page. Here, the second one is microsecond. Okay, there is that. You select to block the parent process for the timeout, and then, well, we add signal to register the signal handler. This one. Basically, when we found a sick child here, a sick child signal, which indicate that the chat process already finished, we execute the signal handler, which basically just print out the goodbye message in here. The parent process should print goodbye. Okay, that is the first solution. And if we take a look at the signal main page here, right? There is a warning that signal system call varies across Unix version and Linux version, so avoid its use and use SIGAction instead. And that is the second solution that I try. It is, instead of using signal, I'm using SIGAction instead. But yeah, we still use select to block the process for the specified timeout here. That is the second solution, and for the third solution, instead of asynchronous using signal handler, I'm trying to use SigWait, this one, to wait for the specific signal set. It is in this case the SigChild signal. There is that. And yeah, we need to make sure that the signal is in the pending list using SigProcMax, because if we didn't put the signal in the pending list, then the SigWait won't know won't acknowledge, is that the word? Yeah. Anyway, the SigWait won't know that the signal already trigger or something like that, if I understand correctly, which might be wrong. Wait a minute. See. SigWait suspend execution of the calling thread until one of the signal specified in the signal set become pending. So if we didn't found the the specified signal in the signal set in the pending list, right? Then the SigWait will suspend the execution indefinitely. I think there is no timeout as far as I understand. So the SigWait will suspend the execution indefinitely if SigWait cannot find the signal from the signal set in the pending list. So there is the third solution, and we just print goodbye, right, instead of using signal handler. Okay, and then I'm trying to use the self pipe trick, like waiting to the pipe and check if the file descriptor already what is it called? File descriptor not empty, something like that. It is using pull one of to wait for the file descriptor to become ready, something like that. But yeah, again, if we take a look at the select, I think it is select here. There is another warning. Select can only monitor file descriptor number that are less than FD set size. It is a reasonably low limit for many modern applications, and this limitation will not change. So there's a suggestion that all modern applications should instead use pull or a pull specific to Linux, this one a pull, which do not suffer this limitation. So instead of using select to wait for the file descriptor, I'm trying to use pull instead. The portable one instead of the Apple, which only Linux specific. Okay, so this is what is it called? This is a blog post about thus closing parent pipe ends automatically close all child ends in C, and it looks like that is not the case, so we need to manually close the pipe. Yeah. Parent-child communication impact. Close it and okay. If the parent closes its write and prematurely, the child can still read until the pipe is empty and a file is reached. Conversely, if the child closes its read end, the parent's write operation will receive sick pipe signal, indicating the pipe is broken. Okay. This asymmetry highlights the importance of coordinating pipe closure between parent and child process to avoid error or deadlock. To manage pipe communication effectively, follow this step. First, define clear roles for parent and child process. Parent writes, child reads. If I understand correctly, in the self-pipe trick, the parent is actually the one who reads the file descriptor, and the child process is the one who writes into this file descriptor. Second use, okay, goes explicitly in its process to shut down unused end of the pipe. Third, ensure both process handle and a file gracefully, especially when reading from a pipe. For instance, use read in a loop until it returns 0, indicating an off file. A common pitfall is assuming that closing a pipe end in one process affects the other. This misconception can lead to resource leak or unexpected behavior, right? Which is basically a bug, right? For example, if the parent closes both ends of the pipe before the child reads, the child will immediately receive an off file, potentially losing data. Always verify which process is responsible for closing its end and ensure closure align with the communication flow. Again, that make me wonder if we return from the chat process, are we not closing the file descriptor in this chat process? Let me check. From that process, that file descriptor close. From this blog post, I assume it is not, but yeah, I'm still not sure. A simple producer-consumer model, the parent producer should close its write and only after sending all data, while the chat consumer closes its read and after processing all input. Thus make two can redirect pipe ends to standard input-output stream, STT out, right? Simplifying communication but requiring careful management of closure. By understanding this dynamic, developer can avoid common errors and ensure robust inter-process communication. Okay, closing one end of a pipe in the parent process does not inherently close all ends in child process, but the behavior depends on the operating system and how file descriptors are handled. The descriptors are duplicated across parent and child process upon fork, meaning both share the same. Okay. My internet connection dropped. Well, let's just hope it didn't go down. Meaning both share the same underlying resource. If the parent closes its end, the child's end remains open unless explicitly closed. This is because the kernel tracks the number of open references to the pipe. The resource is only released when all descriptors are closed. For instance, in a C program, closing the read end of the parent will not affect read end. Open file in the kernel file description table. Okay. The file descriptor to the pipe are closed and thus the pipe will no longer exist. After a fork call, since the child process inherits the same file descriptor and state of the parent, the child file descriptor should be the same in as the parents. Okay, so by that logic, my connection go back to normal. So by that logic, if I close the read end of the pipe in the child, I believe it will also prevent the parent from accessing the file. In this case, it seems very unlikely that this is the actual case, since it will cause the file descriptor between parent and child to be difficult to use, especially since you don't know which process will run first. So So if this logic is incorrect, ask the file descriptor to pick it on fork. How in the file descriptor table are the parent and child file descriptor related? Especially between close call, it has me a lot to be able to draw out the file descriptor table, so I would make as specific as an answer as possible. Now what the status in the way of closing file affect just the child copy of the file descriptor without affecting the parent's copy of the file descriptor. However, immediately after forking both set of file descriptor in parent and child, refer to the same set of open file descriptor. Note the descriptor versus description terminology. Is that different? If the child does things such as read or seek that affect the file descriptor, then the child's activities affect the parent too. To the same set of open file description. Open file description. Let me check. C programming file descriptor versus file description, I guess. There is file pointer. I don't think that's the right. Okay. Nothing changed. Okay. The first concept is a file descriptor. It is a positive integer number used by file system call instead of file path in order to make a variety of operations. Every process has its own file descriptor table. See image 1 below. The main idea of the file descriptor is to decouple a file path, or more correctly, an inode with minor and major the file's number from a file object inside process and the Linux kernel. Let me put this in the chat in case anyone wants to take a look. This allows software developer to open the same file an arbitrary number of times for different purposes. Okay. To decouple a file path from a file object inside a process and the Linux kernel. Direct sync open. Okay. A program wants to read from and write to one file into separate place. In this case, it needs to open the file twice. Thus, the new file descriptor will refer to second different entries in the system-wide open file description table. to one file into spared place, in this case it needs to open the file twice, those two new file descriptor will refer to two different entries in the system void open file description table. In turn, the open file description table is a system void kernel abstraction. It stores the file open status flag and the file position. We can use lsec to change this position. Frankly speaking, there is no such thing inside the Linux kernel where we can find the open file description table. To be more accurate, every create process in the kernel has protect struct, tag struct. Okay, this struct has a pointer to another structure called file struct, and that contains an array of pointers to a file struct. This final struct is actually what holds our file flags. Okay, a current position and a lot of other information about the open file, such as its type, inode, the voice, etc. Are such entries among a running thread are what we call the open file descriptor table. Current position. So now let's see how we can create entities in these two tables in order to create a new entry in the open file description table. Okay. So we share the same file description, but we have different file descriptor. Is that it? Interesting. To create a copies of a file descriptor. Okay. Alright. If the child does things such as read or seek that affect the file description, again, the file description, not the file descriptor, then the child activities affect the parent too. Oh, maybe that is why we can write something in the parent process and the chat process can read the content, right? Because of the share file description here. Especially the execve. So I assume that, what is it called? There is, okay, the parent and chat processor pipe file. Okay, let me try. Conservative table. Okay. Read will return 0 immediately. Okay. Yeah, I mean, I also want to try handling to write error, but yeah, I'm not sure when to write system call will return error. My transfer fewer than count bytes. Successful write my transfer fewer than count bytes. Such partial writes can occur for various reasons. For example, because there was insufficient space on the disk device to write out the request byte, or because a block write to a socket pipe or similar was interrupted by a signal handler after it had transferred some, but before it had transferred of the request byte. In the event of a partial write, the caller can make another write call to transfer the remaining bytes. The event of partial byte, to transfer the remaining byte. Oh, interesting. The subsequent call will either transfer further bytes or may result in an error. That is, if the disk is now full. If count is 0 and FD refers to a regular file, or it may return failure status if one of the errors below is detected. If no error are detected or error detection is not performed, 0 is returned without causing any other effect. If count is 0 and FD refers to a file other than a regular file, the results are not specified. Okay. Implementation defined. Refer to a file other than a socket and has been marked non-blocking and the redwood block. For both possibility, either error to be returned. This can does not require this constant to have the same value. FD is not a valid file descriptor or is not open for writing. Right. I think this is the byte file descriptor, something like that. Okay. The call was interrupted by a signal before any data was written. There's quite a lot. A pipe or socket was reading and is closed. Reading and is closed. Reading and is closed. Interesting. because I tried this, right? Okay, I'm closing the read end, and it's still not an error, I assume. Negative one is returned, right? So there is that. Okay, let me try reading this. In Unix like operating system, inter-process communication is a cornerstone of building complex application. One of the most common PC mechanisms is the pipe, which allows data to flow between processes in a unidirectional manner. But to use pipe effectively is critical to understand how process, specifically parent and child process created via fork, interact with file descriptor that represent pipe endpoint. The pipe endpoint, okay. Common questions arise after parent process create a pipe and fork a child process. Does the parent and child process share the pipe file descriptor? This answer is nuance involving how fork copy resource and how the kernel manage open file object. In this book, I will demystify this behavior with detailed explanation on and a hands-on G-code example. Let me put this in the chat. The process fork and pipe. What happened to file descriptor during fork? Pipe file descriptor parent versus child after fork. Child pipe file descriptor, okay. Independent unit of execution with its own memory space, register, and system resource. Its process is isolated by the kernel, meaning changes to a parent process memory are not visible to its children and vice versa, unless explicitly shared. The fork system call creates a new child process that is nearly identical to its parent. Okay. Its own memory space, register and system resource, isolated by the kernel, meaning changes to a parent process memory are not visible to its children. Process memory are not visible to its children and vice versa, right? So the parent and child process have its own memory space, register, and system resource, unless explicitly shared. The fork system call creates new child process that is nearly identical to its parent. The child inherits the parent's code, data, heap, and stack segment as copies, not shared due to copy on write optimization. The parent code, data, heap, and stack segment, okay. Critically, it also inherits copy of the parent's open file descriptor. Pipes is a kernel managed buffer that enables unidirectional communication between two processes. Yeah, that make me kind of curious. Where is it? I think this one. Oh no, this homework one. Trying to access, what is it called? A variable, I guess. Yeah, if I do this, let me compare that. Okay. Oh, not S2. It's one. Okay. Okay. What about if we use static? Still the same. Okay. So it is not affected. So we are not really sharing the variable from the parent and what is it? Parent and child process. Just something to keep in mind. Yeah. That is interesting. I mean, I'm trying to think about handling the red error, when the, what is it called? When the write system call fail, right? What should I do? Something like that. I mean, I can print out a message, I guess. But then what is it called? The read end of the pipe in the parent process. What should we handle that? I mean, how should we handle the read end of the parent process? Kernel managed buffer that enables unidirectional communication between two processes. It has two endpoints, a read end used to send data into the pipe, a read end used to receive data from the pipe. Pipes are created with pipe system call is returned to file descriptor, read end of the pipe and read end of the pipe. What happened to file descriptor during fork? Okay, to understand the behavior after fork, we first need to clarify how fork handles open file descriptor. Every process has a file descriptor table, a per process data structure that maps integer file descriptor numbers, 0 for recipe in, 1 for recipe out, to open file descriptor in the kernel. An open file description is a kernel manage object that tracks. See, there's a subtle between file description and file descriptor. Every process has a file descriptor table, a per process data structure that maps integer file descriptor number to open file description in the kernel. An open file description is kernel managed object that tracks the underlying file or resource. Okay, the current file offset for seekable resource. The current file offset flags. Okay, reference count, number of FD pointing to it, number of file descriptor pointing to it. Oh, okay. Nine file resource. That is why we can open the same file on different program, I guess, because we share this file description, right? The current file offset for seekable resource flag, and then this one, reference count, number of file descriptor pointing to it. How for copies file descriptor? When fork is called, the chat process receives a copy of the parent's file descriptor table. Okay, the chat process receives a copy of the parent's file descriptor table. Okay, the entire table. Alright. The file descriptor number. Yeah, that is why we have the same file descriptor number, right? Where is it called? When we tried this one, pipe with fork. Let me check. Right, we have the same file descriptor number from parent and child. But yeah, it didn't really think clearly beforehand that even though it is written with 69 exit code, there is no way to check that in this, what is it called? In this parent process. The file descriptor number, for example 3 and 4, are identical in both parent and child process. However, these copied file descriptors reference the same kernel open file description, right? So we have shared file description for different file descriptor. In other words, the parent and child have shared file descriptor table, but their entries for the same file descriptor numbers, number point to the same underlying kernel object, a pipe endpoint. Okay, the kernel's open file description reference count is incremented by 1 for each copy. Okay. I mean, if I open a new file in the chat process, is the file descriptor on the parent process gonna get updated? I mean, maybe something like this. What is it called? Parent, right? Parent process, and then chat process, open file, descriptor, 3 is parent process also open 3, not open file. Yeah, like it is, what is it called? Synchronous, maybe. I don't think that's the right word. See, if the parent process does not open the file descriptor, and then the chat process open this file descriptor, is parent process also open this file descriptor too? After the chat process I mean, is it always get updated? Yeah, I'm still not ready yet. I assume it is not, because they have their own memory, right? And system resource. So it is independent, I assume. Maybe no. Question mark. Yeah, I need more info. Okay. The chat process receives a copy of the parent's file descriptor table. The file descriptor numbers identical. Okay. The kernel open file description reference count is incremented by 1. Application of share open file description. This sharing has critical consequence. The parents modify the file offset. The chat will see the updated offset since they share the same open file description. Closing a file description in one process does not close it in the other. If the parent modifies the file offset, the chat will see the updated offset since they share the same open file description. Closing a file description, closing a file descriptor in one process, for example, parent close the inlet of the pipe, does not close it in the other, ZFT1 remains open. However, it decrements the reference count of the kernel object. When the reference count drops to 0, the kernel closes the object. Okay. Now let's apply this to pipe. Suppose a parent process. There's a pipe with pipe FT yielding read n and write n. Fork that process with fork. But the parent and Z have copies of K. This FT reference the same kernel pipe object, meaning data written to the right end of the pipe, but the parent is visible to the Z reading from the read end and vice versa. The pipe's buffer is sealed between the parent and child. Why close unused pipe end? Pipes are unidirectional, so typically one process reads and the other reads. To avoid bugs or unexpected behavior that is blocking indefinitely, unused pipe end must be closed. If the parent writes to the pipe, it should close the read end, and the child should close the write end. If the child writes, it closes the read end, and the parent closes the write end. Why the kernel only send end of file to the read end when all write ends are closed? All write ends. Okay. If the parent forget to close the write end, the child read will call block forever, waiting for more data even after the parent exists. After the parent exit, set pipe file descriptor. We will create a pipe. Let's validate this with a C code example. We'll create a pipe for a child and show that data written by the parent to the pipe's write end is readable by the child from the read end. By the parent to the pipe's write end. Okay. Okay. Pipe file. Okay. Okay, fork file. That process. Read. Okay. Bytes. Where is byte? Oh, this one. Okay. Alright. Okay. Oh, why is it? Why do we need to add -1 in here? Is that for the, what is it called? The null terminator? Oh, I guess so, right? Null terminate the buffer for printing. So we add the null terminator manually in here. Okay. Set receive. Yeah. This example didn't check whether write system call fail or not. And of course, using wait system call. Okay. Create a pipe with read end and write end. Create a chat process with copies of. Okay. Cause the unused write and reads from pipe. Okay. This one cross the read end of the pipe. In the sense that they're copied file descriptor reference the same kernel pipe object. If the parent writes, it close the read end and the chat close the write end. The kernel sends an off file to the read end only when all write end are closed. Forget to close write end cause it to block indefinitely. Where is it? The chat successfully read the message written by the parent, proving that the pipe FD are shared. They reference the same kernel pipe buffer. The read and okay. Copies file descriptor, but the underlying kernel file object are set and enabling inter-process communication. Okay. Yeah, that make me kind of wonder how to handle the write system call. Guess what? You learn don't get used. Don't get used by you. Use what you learn. Don't get used, but you yet don't know. Oh, okay. Yeah, I'm just wondering, That's kind of make me curious, I guess. The save pipe tree. Hold on a minute. So we keep trying to write even when what is it called? When we got an error, but yeah, let me check. The call was interrupted by a signal before any data was written. Oh, okay. Before any data was written. Let me check. Where is it? Self-pipe trick. Okay, So I need to use it. Yeah, I don't think we need this one. But I want to make. Let me move this into another file. Maybe something like this. No, not that one. Okay. The difference between using initialize. Okay. Let me check. Signal init. Okay. So yeah, let me try this out. But with fog, right? Pipe FT, because we populated in the pipe here. Pipe FT, if it is equal -1, then we throw an error. Let's see, fork. Trying to fork here, right? So I try to use switch instead of. Yeah, let's try using switch, I guess. -1 means there is an error. Fork error return 69. If it is 0, then it is what is it called? The chat process. Because FT yeah, I want to write in the chat process. process. I want to write in the chat process. Yeah, let me try to check. C programming get chat process return exit code method with PID. I'm wondering if we can, yeah, I know that we can get the exit code of the chat process using with or with PID system call. But currently the constraint is without using with or with PID system call in the parent process. So I need to be creative there, you know. Yeah, can we like do that? Oh, be open. Yeah, a lot of article is using with or with PID. I mean, again, if let me close. With pipe error. Child cross with pipe error, maybe something like this. 1069, okay. The signal number, Maybe I should put this before in this one, maybe signal 0. And then replace that in here. But yeah, if I do this, let me try. But we are only reusing the variable signal here, which means that we need to put this in the right, in the pipe, I guess. But yeah, is there any, wait, see, check list. Oh, not in this one. Check it's up. Is it the... Yeah, I'm kind of curious. Is there a signal that equivalent to 0? Let me check. Size of... Okay, call negative 1, right? Process write error. Yeah, let me check in here first. It's 1. S3 self-pipe trick. Something like this. Okay. Right. I think I need to add in STT. Self-pipe. Oh, sorry. I should have done this instead. Yeah, I want to check the macro of signal. Okay. Sig edge up is 1. What about sig in drop? Where is it? Oh, sig interrupt second. Okay, so I assume there is no 0 signal. If that is the case, then we might be able to use that. Signal with 0 code. Alright, well, let's continue this first. And then close, right? Process. Cause an error. Read pipe error. Right, pipe error. Okay. Return 69. Don't forget to add break. I mean, in this one we already return, right? After then break. This is the parent process. Fault 1. We are closing that. I don't plan to write in the parent process. Let's close that. Pipe error. And then return 69. Afraid. If I'm only doing this, right? Oh, it is waiting. But yeah, let's try not using wait, but only what is it called? Only using read in here. Read. Read error, I guess. Something like that. I want to print the signal. I don't think. Oh, interesting. If you omit this, okay, now what happens if we didn't close the pipe? Interesting. Alright, I forgot to add break. It has some sort of safety cut, I guess. Let me think. So if let's say that let's say I print in here hello, and well, goodbye in here. Is it always guarantee that we will print like that? I am not sure. Let me check the poll sample here. Error poll. Poll lefty. Okay. But then that's available now. Okay. Wait a minute. Red, okay. F count is 0. Oh, wait a minute. An error -1. But 0 indicate end of file. Okay. 0 indicate end of file. Comments at the file offset and the file offset is incremented by the number of byte read. May detect the error described below. If it does not check for error, Return 0 and has no other effect. Okay. Do we need to use pull to wait? Maybe. Okay. Let me check. If this argument. One of a set of descriptor to be come ready to perform input output. Oh, right. Wait a minute. Okay. This one, right? Cause red pipe error. Is there any guarantee that we will always print the chat process first? Until what is it? Descriptor ready, I guess. Blocking call for reading file descriptor. Block until further. It's not that safe in case there are other tabs operating on the same file descriptor. Initialize the pull set to add the file descriptor you're interested in. For the current cell file descriptor, when pull returns, scan the event and find all of the file descriptors that are ready. Remove them from the pool set. If there are any file descriptors still in the set, go back to step 2. Maybe data available now. If signal equal the child, then goodbye. Is using read here enough? Or do we need to use poll? Yeah, I'm still not sure. I guess to handle right failure case. Take any guarantee that read will read the content of make sure check process finish. We will wait until it got the descriptor content. Size T, read, pattern code read, okay. I see read, okay. Yeah, I'm kind of curious. We can use this one. Maybe something like this. Okay. Long in, okay. This one. SIST aka also known as long in. Okay. Something like this. Four. Okay. If I try something like this, bed file descriptor, okay, and there is hello. Transfer Atmos, okay, and the number of bytes actually transfer. Read fee. What is read fee? Into multiple what? Into multiple buffer. Okay, interesting. And it looks like this is POSIX, I guess. Read vector. Okay, let me check this one. Yeah, if I understand correctly, this example it is not used in okay. Wait indefinitely. Dispatching. using pull to read, and then using read to read the signal. But why are we using wire? Why is this using wire? Handler, dispatch, okay. I mean, maybe. Maybe we should use pull in here. But yeah. Using pull to read. Come on. Okay. So let me try using pull. Wait a minute. Maybe can try using sleep, right? For 5 seconds. Oh. Okay, that is interesting. So is there a guarantee that it will wait for the file descriptor to have a content? I mean, again, if we didn't have all of this, maybe except for this. we wait for no. Okay. Yeah, right. We didn't wait for the child process. Interesting. Yeah, previously we already checked what this one parent process finished before the child process. So the child process will become orphan process, which means the PID1 or the init system will take care of that, will take over. I forgot how many seconds? Oh, 20 seconds. Okay. Okay. See, there is a delay or something like that, which look weird, right? This is the comment that I typed, and this is the output of the chat process. And yet the parent process identifier is 1 instead of this one, right? We change the parent process. That is interesting. Okay, let me check again. Okay. All right. Okay, is there any guarantee that read will wait until it got the file descriptor content? Still not sure, but when we add sleep in the child process, we are waiting for the sleep to finish. Okay, let me try moving the sleep after the print. Hello here. Okay. And then again, maybe in here. All right. Okay, so after we write, after we write to the file descriptor, the sleep did not get triggered. See, if we put this after this, right, after painting hello and before write this one, before write to the pipe file descriptor, the sleep for 5 seconds will get triggered, not skip, Interesting. Okay, then we can use this, right? Sleep. Sleep before right in the chat process. This is the total time, around 5 seconds. Now alright, I haven't recompiled. This is without sleep for 5 seconds. Okay. That is quite interesting. This will be executed. Not really like that, but yeah, let me add brain second sleep. Okay. After second sleep, right? That is quite interesting. I'm not sure how to explain this, but if we didn't write, oh, okay, after second sleep. Interesting. Let me see. Okay. What happened if we didn't close the pipe? Interesting. So maybe, yeah, let's try not close the right end of the pipe. Is it gonna hang up? Okay. That is interesting. Yeah, it's kind of waiting indefinitely until it found an off file, I guess. Right? But yeah, that kind of interesting. I mean, yeah, is it a coincidence? Maybe. I'm still not sure. Okay. Before right in the third process. Yeah, I mean, maybe store it up to count bytes from file descriptor into the buffer starting at buff. Okay. Up to count bytes. If the file offset is at or past the end of file, no bytes are read and read return 0. On file type support checking, and the file offset is incremented by the number of bytes read. If the file offset is at or past the end of file, no bytes are read. Is that a coincidence? It is not an error if this number is smaller. Let me try this. Yeah, that make me wonder. Do we need pull to with the file descriptor? Let's add that to I guess. Try using pull. Pull with right. Maybe someone already asked that. From scratch whether your file descriptor are available for writing. Doesn't do linear scan afterwards file descriptor. Scans file tolerance number, okay. On any Unix system or maybe POSIX system. Okay. Police POSIX standard interface. They tell you which one have data available to read or write to. Select just tell you there's input or output error. Which file descriptor to monitor? Yeah, maybe we will try using pull because I am not sure if read will, what is it called? If read will wait for the chat process to finish. Or maybe it will. Yeah, that is interesting. another maybe you can maybe let's just split this out, something like that. There's an implementation that use read, only read, and also implementation that use pull. In another file. Yeah, maybe let's try to split that up. I mean, again, I'm not sure if we need to use pull in this case, but at the same time, I'm not sure if we have any guarantee that read will wait the file descriptor, or maybe wait until we got the, what is it called? We got the end of file in the file descriptor. Yeah, well, let's see. Let's explore that in the next session. So I guess that's it for now. Thank you for watching and see you next time. Bye bye.